So 147. So we talked yesterday about parametric equations, and they're used to describe horizontal and vertical components, where we didn't get that all the time from just using normal functions like you're used to. And the parameters are arbitrary values, usually time or angle measurement, but not always, because it could be temperature, it could be other things, but we use t no matter what the parameters are. So we're going to start, I guess I could have had you do this while I was stumbling through everything else, but this is pretty much just like what we did yesterday. So we will start here, sketch the curve given by each pair of parametric equations over the given interval. So they give me the interval from -4 to 4, so I'll start from -4, -2, -1, 0, 1, 2, 3, 4. Okay, so we got some extra spaces, and that's okay. All right. So when I take that 4, I'm going to substitute it in for my x. So -4 squared is 16 plus 4 is 20. Then -3 squared is 9 plus 4, 13. -2 squared is 4 plus 4 is 8. -1 squared plus 4 is 5. 0 squared plus 4, 4. 1 squared plus 4 is 5. 2 squared plus 4 is going to be 8, and then 13, and then 20. Okay? Oh, good. Sorry, I was looking at a different problem up there going, why do our numbers look different? It's a different problem. All right, so then I'm going to do the y. So for y, -4 divided by 6 is like -2/3, right? And then -2/3 minus 3, -3 2/3. I am not a fan of mixed numbers really at all, except for cooking, if they're given to you, and if you're going to just use it on a graph like this. Otherwise, improper fractions is where you want to go, but really that would be something that would be kind of easy for me to plot. So we're good with that one? Okay. So then -3 divided by 6 would be -1/2, right? Minus 3 would be -3 1/2. Then -2 over 6 would be -1/3, so it would be -3 1/3. -1 over 6 is -1/6, -3 1/6. So this would be 0 minus 3. So then 1/6 minus 3 is going to be a -2 and what? 5/6. Good. It's all good. We can handle this. All right. Then 2 over 6 is 1/3. So 1/3 minus 3 is going to be -2 and 2/3. Okay. Then 3/6 is 1/2 minus 3 is -2 and 1/2. 4 over 6 is 2/3 minus 3 is -3 and 1/3. So look at your y values. They're all very, very close to each other, right? Which means we're not going very far on the x, and I kind of wish this graph was a whole lot different than it is right now, but that's okay. It's going to be kind of squished. So we're going to plot this. At 20, I am at -3 and 2/3. So -3 and 2/3 would be right about there. Okay. Then at 13, which this would be 14, so 13 is right here, I'm at -3 1/2, so I'm about right there. At 8, I'm at -3 1/3, about right there. Then at 5, -3 1/6. And then at 4, I'm at -3. I don't know how accurate my stuff looks, but it's close. Then I've got, at 1, I'm at negative 2 and 5, 6, which is almost 3. So at 1, right here, probably have everything a little bit high, but it's fine. We'll get the idea. 2, I'm sorry, then I'm here at 1. So then I go, wait a minute, I graphed the wrong thing, didn't I? Crap, I'm not graphing 1. Dang it. Nobody stopped me. Y'all were just like, yeah, I like that one. I'm plotting these. I'm not looking at those anymore. I'm going back to, I was at 4, I'm going back to 5. And now at 5, I'm at like 2 and 5, 6. No one's going back, just one going back yet. That's a little too high, but it's okay. And then at 8, like right there, 13, like right there. Y'all didn't stop me when I plugged in 4 either. What's wrong with my 4? What's wrong with this? It should be 2 and a third. Because 4, that's 2/3, yeah. Negative 2 and a third. So at 20, like right here. So this is like a really skinny looking curve this way, right? Looks something like this. Oy. Mine shifted up a little bit, but I didn't want to start over, so you get the idea. Now, we need arrows, right? We started on the bottom half or the top half? The bottom half. Here we were at when time was negative 4, right? And, or whatever t is, it's not necessarily time. And then it went like this. Now remember, the idea of the parametric equations is that it actually represents the path of whatever may be happening, and it may not be something that's actually moving, but something could be moving along this path and back and forth. Okay, so I start here and I go this direction, then I come back. And your distance here is even negative. Let's think about it as distance, all right? We can think about this maybe here being sea level, okay? So that's sea level, and here's a fish under the water. And we're talking about the distance from us and the distance from the top of the water. So the fish could start over here. He could swim towards us as he's getting closer to the top of the water. Then he turns around and he's still getting closer to the top of the water and goes back away from us. Okay, so do you see that actually represents a path instead of it always having to go forward because it's totally time. You can go back and forth on a parametric, which kind of makes some of the stuff pretty interesting when we apply it, which we'll look at applying it. So it's not all just arbitrary. All right, we're good with that. Can you graph it? If you do the math right and without me, maybe that'd be better. So now let's just look at this one. It says use the parameter to write the parametric equations that can represent each equation. Now this is the one this is the part where it did say then graph, but there was no interval. And there was I cannot find any explanation on how you're supposed to know without guessing and checking, and I am not a fan of that. So we're going to use the parameter. This is our parameter, our time, our temperature, our whatever that is related to x, and this is our y. So all you're really doing here is substituting, okay? So we are going to use the parameter to write the parametric equations that can express each equation, which means that we are looking for an x equals and a y equals, both in terms of t. Okay? Now my x already has a t involved with it. Y does not. So I can take this one and I can solve this for x to get it in my x equals. You agree with that? Pretty easy to solve? So this can become t minus 8 over 4, and that's equal to x. You good with that? I just solved it all in one step. You just subtract 8, divide by 4. We're good? All right, so t minus 8 over 4. We could simplify that, but I'm just going to leave it like that for now. Then we're going to take it and we're going to substitute this in here for x. It's kind of the opposite of eliminating the parameter like we looked at yesterday. So we're going to get y equals t minus 8 over 4 squared minus 1 all over 2. So I'm going to square this. T minus 8 squared is going to give me t squared minus 16t plus 64 all over 4. No. What do we do with that denominator? Square it. It's not 4 anymore. It's what? 16. Oh. There you go. Over 16 minus 1 all over 2. Right? All right, so then, can I simplify this out here a little bit? Yes? So this can become 1/16 t squared minus what? I'm just going to simplify this. T, you can divide that by 16. How many times does 16 go into 64? 4, right? Plus 4. Then minus 1 all over 2. So then that means that y equals, I want to get it all up, don't want the fraction and a fraction idea there. So what's 1/16 divided by 2? 1/32. So 1/32, 1 over 32, t squared minus 1/2 t, and then plus that positive 4 and negative 1, this actually gives me a positive 3, right? So this will be plus 3/2. So there's your y version there. 1/32 t squared minus 1/2 t plus, it's just substitution to get them into your y equals, and you are given both of these, and I'm not going to make you graph them until I can explain to you how you're supposed to know the interval when somebody doesn't tell you. And I don't think you do know the interval, because that's the whole point, is you're applying it to something on some interval. There should be no reason to guess. We good? All right, now let's look at how we're going to solve some of these using calculator. All right, so parametric equations are often used to simulate projectile motion, and that is how you would have used something similar to this. It's not similar, it's the exact same thing. You just may have called it some different things in physics, because I know you talk about projectile motion a lot in physics. Okay, so for an object launched at an angle theta, so an angle with the horizontal at an initial velocity of v sub 0, that's your initial velocity, where g is the gravitational constant, and it's a constant, so should you know what it is? What do you use for your gravitational constant in physics? Okay, 9.8 meters per second squared. Okay, now, unless it tells you what? Okay, but here, we're going to be talking about feet, so I really think that we should be consistent. I know why you use meters in physics, because it's kind of universal, and then, you know, the different types of measurements aren't universal. But when we use feet, our gravitational constant changes, so just know that. It's still a gravitational constant. It's not that you get a different one in physics than you do in math. It's that in physics you're using meters per second squared, and in math right now we're using feet per second squared. Doesn't mean you wouldn't use meters. Okay, so it is the exact same thing, because gravity is gravity, and I just want to make sure you understand that. Okay, all right. So g is the gravitational constant, and t is time, and h sub 0 is the initial height. Okay, the horizontal distance x can be found by x equals t times v sub 0 cosine theta. So it's giving us what our generic equations look like, and the vertical position y by y equals t times v sub 0 sine times sine of theta minus 1/2 gt squared plus h sub 0. You don't have to memorize it, you just have to know that these don't change. This is given to you on how you make them, okay? So we're going to use this, and we're going to look at Luigi. So Luigi is kicking a soccer ball. He kicks the ball with the initial velocity, so we need this, initial velocity of 35 feet per second. Okay, I lost the second part there. And an angle of 48 degrees. So we have our initial velocity, and we're using feet per second. That's how we know we have to use a different g. And our angle of 48 degrees with the horizontal. The ball is 2 feet above the ground, so that's our initial height when he kicks it. How far will the ball travel horizontally before it hits the ground? So we're going to make a little diagram. Okay, so there's Luigi. Okay, with his weird leg, his weird kicking leg. All right, and he's going to kick this ball. Here's the ball that he's kicking, and here's the ground. All right, so it tells me that this is initially 2 feet above the ground, right? This is the angle at which he kicks it. That is 48 degrees with the horizontal. And his initial velocity is 35 feet per second. Okay, everybody good with that? You can always feel like, your pictures are better than mine. But there we go. So we're going to write a parametric equation for the vertical position of the ball first. Okay, vertical position of the ball. So our initial velocity, they gave that to me. It's 35. Theta, they gave that to me. It's 48. G, since it is in feet per second, is what our velocity is. It is 32. Almost put 35. Excuse me. And then my initial height is 2. So those are all the things that I need to be able to go and substitute it in. And I am substituting it into this right here. Okay? And I'm going to scroll back up, but that's where I'm getting this stuff from. Actually, I put it right here. That's why I did that, so I wouldn't have to scroll. All right, so I'm just going to substitute all this stuff in here. Y equals T times V sub 0, which is 35, times the sine of 48, minus 1/2 times G, which is 32, times T squared, plus H sub 0, which is 2. Now, I could clean that up a little bit, but we're going to use it in the calculator, so it's okay that it's not clean and pretty, because we would really probably write, T would probably not be there, and we could take half of 32, but we're going to let the calculator do some stuff for us, all right? So it says, graph the equation for the vertical position to find blank, and we're going to use that to find when it hits the ground. Okay, so we're going to graph it. There is a way to graph parametric equations, but we're not technically graphing parametric equations here. We're graphing this, which is going to look like what when we graph it? What's the graph going to look like? Like what shape that we know of? A parabola. Okay, we know it's a parabola. And we're going to for t, we're going to use x, and so you're going to graph it like you know how to graph it. I don't know why my calculator's so big here. Make sure you're in degree mode, right? And I'm going to go in here and I'm going to graph this x times 35 times the sine of 48 minus 0.5 times 32 times x squared plus 2. I'm going to graph it. First time I graphed one of these, I got something really wonky, and I was like, what the heck just happened? And I realized I didn't close my parentheses after my sign, and so it gave me something crazy that I knew. Now, I can't see the whole parabola, but I don't really care, right? Now, this is exactly like how you were doing this in Algebra 2 when you were just trying to look at time and height, basically. And I want to know when it hits the ground. The actual question is, how far will it travel horizontally before it hits the ground? That's not what we're finding here. We're just finding here at what time does it hit the ground. So what am I looking for here on my graph? What am I actually going to look for? The x-intercept, right? Not here, because that's at like before 0, right? Since that actually starts up here. But I want this one. Now, how can we do that? Calculate, okay. So second calculate, and what do we want? 0, okay. Now I got to do a left bound and a right bound so I get the correct 0. How do you change your bounds? Like how do I move where that is so I can change where my left bound is? Arrows. Okay, I learned this. I didn't know this until like last year, and I think this is so amazing. Sometimes you have to arrow like forever, right? In your little spider runs. We'll check this out. I know, and I'm never going to use my graph to like guess, but clearly that's greater than 1, right? So my left bound could be 1, and my right bound could be 2. Do you agree with that? So for left bound, when it's asking me that question, if I just hit 1 and hit enter, bam, that's my left bound. And then now it's asking me for right bound, I can hit 2 and hit enter. That like changed my life when I learned that. Bam. And so then it shows you the arrows there too to tell if it's really left bound and right bound, and it can keep you, because have you ever moved your spider and then like it jumps off and you're like, where the heck did he go? Right. Where the heck did he go? I don't know where it is. But so if you kind of know what your bound is, even though you don't know your answer, you got your bound there, right? So now, and my guess, sure, that's my guess, whatever, I don't really care about that. And then bam, we got X, okay? So I found that 0, and there is my X value. Now I know that this doesn't really look like 0, but it really is, and it's fine. So it's like 1.699, right? So when it hits the ground, okay, so we're gonna, let's see, what do we use? Calculate 0. I want to use calculator and calc 0. Right. And so we get that t equals about 1.699. Now, here's the beauty of this as well. I know it's really t. The calculator has used x for it, and that's okay. Remember this. Because this calculated it for me, when I go back here, x is that number. Because on the graph part it said x equals this, it has stored it in x for you. And that's a good thing because we need it stored, all right? We don't have to go and like guess and try and store it somewhere. It's there for me. And you can double check that hit X. If you actually calculated it and you found that 0, then you're good, all right? Because we're going to want that calculated value. All right, so now we are going to write the parametric equation for the horizontal position. Dang it. Horizontal position of the ball. And this is the generic that we use. All right, so our v sub 0, we know what that is, right? It's the same. It was 35. Our theta is the same, which is 48. But for this one, I need the t, right? So that I can write it with just a t, but I know what t is, so I can actually determine the position of the ball. So t here is 1.699 ... So we're going to use that stored in the calculator. When I write this equation, the actual parametric equation is x equals t times 35 times the cosine of theta. But because I determined when it hits, how long it takes to hit the ground, when I substitute in my t right here, then I'm going to get the actual distance it takes before it hits the ground. So in my calculator, I don't have to go graph anything. I'm just going to type in, but I have to use x here because my calculator stored it as x. I'm going to go in here and hit x times the cosine of 48. Nope, times 35 times the cosine of 48. Dang it. Times 35 times the cosine of 48. And what that's going to give me, because it's using my stored value, is the actual distance, which is 39.794. And feet, all right? There's your horizontal distance. All right. Any questions so far? Good. All right, let's look at the next example. It says Julie is throwing a ball at an initial velocity of 28 feet per second and an angle of 56 degrees with the horizontal from a height of 4 feet. Oh, goodness. Well, where the heck is my... Okay, well, how did it just disappear? That didn't even make any sense. right, well, y'all have it on yours though, right? Yours didn't disappear? Okay, good. And I have mine on here, so why it's not up there, I don't know. All right, so Julie's throwing a ball at an initial velocity of 28 feet per second at an angle of 56 degrees with the horizontal from a height of 4 feet. So on part A, it says, write parametric equations to represent the path of the ball. So we're going to use that same generic one over there. Let me just go ahead and write it. Since y equals t times v sub 0 times the sine of theta minus 1/2 gt squared plus h sub 0. Right. So I have, y equals t, my initial velocity is 28 feet per second times the sine of theta, which is 56 degrees, minus 1/2 times g, which is still 32, t squared, plus h sub 0, which is 4. Okay, so here's my y. For x, that is t v sub 0 cosine theta. So x is equal to t times 28 times the cosine of 56. So here are my parametric equations, my x and my y with my parameter of t. Okay. Here's my picture of the ball. There's the ground, and so this is 4 feet. The ball is kicked or thrown or whatever she does. This is 28 feet per second, and this is 56 degrees. Okay, and there's the path of the ball. So it's asking me how far away will the ball land. So what do we have to know to find that? Time. Okay, so the first thing we need is the time, which we don't have, so that we can substitute it into here. So we find the time by doing what? Graphing this, right? So I want to graph this. So I'm going to go back to my calculator, and in here I'm going to change this to x times 28 times the sine of 56, and then that, oops, oh goodness, this is not good, because then this needs to be 4. Notice how I didn't rewrite all of it, or I didn't retype all of it. I just changed. There's only 3 things that have to be changed. This 28, the 56, and the 4. Everything else stays the same. So then I graph it. Now, is there a different way besides using the 0 function that I could have done that? If I know what that is. What if aren't I looking for, since I'm looking for the intersection with the x-axis, aren't I also looking for the intersection with the line y equals 0? I could have graphed the line y equals 0 and looked for the intersection. That works as well, because you're going to have to do that on that last one. I don't want to trace. So I'm going to calculate my 0. My left bound, I can do 1 again, and 2, and then my guess. It's like 1.606. All right, no. Then I'm going to substitute into there. So x equals 1.606, but I'm really using the calculator for that, times 28 times the cosine of 56. So in my calculator, remember, it has stored that x for me. So this is just x times 28 times the cosine of 56. And there's my answer, 25.153 feet. $25.153 feet. Everybody okay with that? Do you understand what we're doing and why? What we're finding here? Okay. Now C says, how long will it take for the ball to travel 12 feet horizontally? All right, so we found out how long it would take before it hit the ground. That's what this is. And we found out how far it will go before it hits the ground. That's where this is. Now I want to know how long it will take to travel 12 feet horizontally. What do you think I could do there? I could manipulate which equation? The x equation, right? So this is how far it travels horizontally, right? And this is the time. So instead of here, I knew the time and I found x. Now on C, you know x, because x is the horizontal distance. It's telling me x equals 12, and I want to know what is t. Does that make sense to you? So when I substitute that in, that's going to give me 12 equals t times the cosine of 56. Oh, dang it, I keep leaving that out. 28, 50, I don't know why I can't do that, times 28 cosine of 56. Which means that t equals 12 divided by 28 times the cosine of 56. Be very, very careful when you type this into your calculator. You need parentheses around that whole denominator there. It's easy to type in, but it's easy to mess up. 12 divided by, open parentheses, 28 times the cosine of 56. Otherwise, it's going to divide by 28 and multiply by the cosine. Hit enter. Bam. So it takes 7.66 seconds. I'm sorry, 0.766 seconds to travel 12 feet horizontally. That's why it is important when you have these equations, you know what represents what, and it's not just you punching buttons, because that way you can go find whichever piece it is that you need. Any questions? All righty. Why does it look